Dear friends and colleagues, ladies and gentlemen, first of all, I want to thank the organizers and especially Professor Herman Tekaya and Professor Paulo Martins for organizing this honorary symposium for me. I feel not only deeply honored, but also very humble towards this special acknowledgement of my work. In the following talk, I will try and present 50 years of research and development in metal forming and joining. Here's an outline of my talk. After co-pressure welding, I'll talk about modeling of friction, development and testing of environmental friendly lubricants in sheet forming, modeling of microhydrodynamic lubrication in metal forming, single point incremental forming, modeling and testing of resistance welding, and finally give some acknowledgements. First, co-pressure welding. I started my research already in my master project in 1971 on co-pressure welding. Pioneers in this field were Dr. Milner and his research group in the University of Birmingham. They were focusing on analyzing and studying roll bonding of similar as well as dissimilar metals. And they were testing the bond strength in a shear test as illustrated in this figure. Here we see the bond shear strength plotted versus the surface exposure for a number of different metal combinations. The surface exposure is defined as A1, the final area of the interface, minus A0, the initial area, divided by A1. And this parameter equals the reduction in thickness. The general trend of these curves is the same. That is, in order to obtain bonding, you need to exceed a certain threshold surface exposure. After that, the bond strength increases rapidly to reach a steady progress corresponding to the strength of the weaker metal. Preparation of the surfaces before roll bonding is typically done by scratch brushing, as illustrated here for one of the two strips. It was originally thought to clean the surfaces, but later studies in scanning electron microscope showed that it created a very brittle cover layer protecting the surface below from oxidizing. Already at diminutive expansion, as seen here, we see cracks in this brittle cover layer. And at further surface expansion of 37.5%, the cracks open and we see virgin material extruding up through the cracks. At just a little bit larger surface exposure, 38%, the first bonds, metallic bonds, have formed to the opposing partner, and they are fractured by ductile necking. If we go to larger surface exposure, like here, 72%, we see numerous bonds, and the original cover layer is now confined to these isolated islands between a big sea of dimple-structured bond fractures. Our first interpretation of the bonding mechanism assumes the two brittle cover layers to cover the entire surface and fracture uniformly. A larger expansion, the underlying workpiece material is extruded through the cracks, depending on the pressure, and eventually reaching the opposing partner. And due to high vacuum in this area in the cracks, these exposed surfaces are completely clean and form metallic bonds. Later observations by us in scanning electron microscope of the scratch brushed layer, as well as of fractured bonds, proved that the bonding mechanism was a bit more complicated. The brittle cover layer was not covering the whole area, but confined to such long tongues, which were really material picked up by each individual wire on the scratch brushing machine or on the brush, and re-welded to the surface with very high work hardening and large brittleness as a result. In between those tongues, we have an area of the base metal, which is soft. Both are, of course, covered with a contaminant film, as illustrated here. And in the area with the brittle cover layer, of course, we have the mechanism I've already explained for bonding, whereas we also have bonding in these areas when the contaminant film is thinned down to create virgin surfaces as well here. Based on the observations in scanning electron microscope, we were able to propose a model for the bond strengths consisting of two terms. The first term is the fracture of the brittle cover layer, where bonding is established when the normal pressure exceeds the pressure required for extrusion through the cracks in the cover layer. This is a function of the surface exposure Y. The second term is bond formation where we only have the contaminant film, and this occurs when the surface exposure exceeds a threshold surface exposure for thinning down the film. As we see here, our theoretical model corresponds well with experiments done on the plane strain upsetting of two aluminum blocks in a channel forming tool. We were able to do experiments at different values for the normal pressure and proved this model to work well. The surface preparation by scratch brushing is, as shown before, a rather rough way of creating a brittle cover layer. We have therefore developed alternative, more reliable ways using electrochemical as well as chemical plating of brittle surface layer. What we see here is an aluminum surface being row bonded after plating with electrochemical nickel. This layer has fractured almost completely brittle and created virgin material or exposed virgin material, which is bonded to the opposite partner, and we see beautiful ductile bonds after stripping the two plates apart. Next item I will talk about is our work on modeling of friction in metal forming. Metal forming is characterized by high normal pressures in the tool workpiece interface. Professor Vanheim and I have proposed a model for friction, including low as well as high normal pressures. The model is based on slipline analysis of the plastic deformation of asperities, here assumed to be longitudinal in shape and with a triangular cross-section, such as a machined surface. They're loaded with a plane tool on the normal load as well as friction by relative sliding. And the real friction stress in the interface is assumed to be constant, namely a fraction of the shear flow stress, F running from 0 to 1. With increasing load, we see increasing real contact area here and here. But at a point in time, the isolated deformation zones begin to touch each other and interact, and it becomes harder to deform the surface of the asperity further. By slipline analysis, we can calculate this ratio alpha of the contact area ratio as a function of the nominal normal pressure, Q, divided by the flow stress of the material. The parameter here is the friction factor, and increasing friction will provide further deformation of the asperities apart from the normal loads forming. A friction model is established by stating that the real friction stress acting on the real contact area should equal the apparent friction stress tau acting on the apparent contact area A. And by this, we get this model tau equal to F alpha K. Utilizing these results for the alpha value as a function of the normal pressure and friction factor, we can determine the friction stress. And here we see the normalized friction stress, tau over K, versus the normalized normal pressure, Q over the flow stress. The friction factor is the parameter. We notice that at low normal pressures, below 1.4 times the flow stress, we have a linear relationship between friction stress and normal pressure. That is, Coulomb's law applies. At higher pressures, the curve goes towards a constant value, since the value alpha goes towards unity when pressure goes towards infinity. And this corresponds to the often applied constant friction law applied in bulk metal forming operations. We have set these curves on a mathematical formula. At low normal pressures, of course, we have proportionality between tau and Q when Q is less than the limit of proportionality in normal pressure. At higher normal pressures, tau equals an exponential function of Q, in which Q star and the limit of proportionality in tau star also are involved. And these limits are easily calculated using slipline theory. Here we have tau star over K as a function of F and Q star over the flow stress as a function of F. We realize there are limitations to our model, especially the fact that we do not take subsurface deformation into account, and we only take strain hardening into account in an average sense. Much later, we established a project with Chris Nielsen as postdoc, Paulo Martins and I, and we were aiming to solve these deficiencies by establishing a fine element model of the asperity deformation, taking subsurface flow into account. Before showing the calculations, I will show our experimental setup for verifying this model. We use this dog bone geometry with a central part of an aluminium block provided with asperities, longitudinal ridges with a triangular cross-section. Here we have 26 asperities, and they are inserted into a channel forming tool and loaded by this tool fitting into the channel. Under superimposed tension, whereas we can also do the same experiments under superimposed compression. Then we use this setup or this geometry of the specimen. So the parameter which we are altering here is the longitudinal strain, which is much larger, of course, in tension using this setup than when we superimpose compression. Up here is shown the fine element model of the asperity deformation. And down here we have plotted the real area of contact versus the longitudinal strain with the normal pressure as a parameter. Q is normalized with the value C in Holloman's expression, which is, of course, the flow stress at unit strain. We see that for all three cases with three different superimposed stresses, we get good accordance between the FEM model and our experiments. This shows a full map of the numerical model for the case of aluminium 1050 in a new condition. So we have the real contact area ratio versus the subsurface longitudinal strain, where the black curves here corresponds to limited normal pressure, where we have tension superimposed, and the gray curves corresponds to superimposed compression. You could say that the black curves corresponds to sheet metal forming and the gray curves to bulk metal forming. And it's worth to notice that especially in tension, we see a significant influence from subsurface longitudinal strain. This is not so much the case in compression, only in the first little deformation part. The next issue I'll touch upon is development and testing of environmental friendly lubricants for sheet metal forming. Industrial stamping production of ultra-high strength steel, stainless steel, and titanium alloys requires environmentally hazardous lubricants such as chlorinated paraffin oil. Danish industry, who has important sheet forming production in stainless steel, was already in the 1990s aware of the environmental issues due to this and looking for new environmentally benign lubricants. In 1994, we established a collaborative project with them on developing and testing such lubricants. Much later, in 2006 to 2007, EU introduced new legislation in form of the program REACH, aiming at high level of protection of human health and the environment from risks posed by chemicals. As an example of our work with industry, we have here an industrial case study done together with Grundfos, where stainless steel tube is formed with a flange, is formed in a progressive tool, starting with punching out or blanking the initial workpiece, deep drawing, redrawing, and a second redrawing, sharp pressing of the flange, and finally punching out the bottom. Especially during the second redrawing, we have tripologically difficult situations, demanding that we use chlorinated paraffin oil in order to avoid galling. Our aim was then to find an alternative to this lubricant. Online production testing a new treatment system is costly and unflexible. Offline production gives much higher flexibility. In the present production case where we have deep drawing and 2 times redrawing, it's natural to use the bending under tension test as a simulative laboratory test to emulate the conditions in the drawing radius here. Here we see the test tool which we have developed for bending and tension. We have a 2-pin, the red 2-pin here is cylindrical, circular cylindrical. It's embedded in a cradle here, the green cradle, which can rotate freely in 2 side tools by needle bearings, but is prevented from rotation by this piezoelectric torque transducer, so that we can actually measure friction directly in the interface. We also measure the front tension and back tension by strain gauges mounted on these webs in horizontal as well as vertical directions. Here we see the webs more clearly, and the pin tool is mounted here. We are able to preheat the 2-pin to a maximum of 150 degrees C using electric heat cartridges. We can also heat by water, warm water, of course not to the same temperature. The plots we see here show results on testing stainless steel with plain mineral oil without any additives. We see that if we run the test at 20 degrees tool temperature, we have a very stable front tension, and the yellow curve back tension, and the red curve representing the torque. If we increase the temperature to 45 degrees, we see the torque increases quite substantially due to lowering of the viscosity and thereby thinning the film. At 60 degrees C, the friction continually increases, and eventually we get stick-slip condition. And at 70 degrees C of tool temperature, we get stick-slip immediately. These results then indicate the importance of performing laboratory tests under conditions simulating the production. If the simulative tests were done at room temperature of the tool, the lubricant would have been approved for production. But since the production is running at high rate with 40 strokes per minute, the tool temperature will increase to a level of typically 70 degrees C, and it's vital to carry out the simulative test under similar conditions in order to obtain useful results. In order to design the laboratory test, it's therefore necessary to analyze the actual Triebe conditions in the production. And especially 2 parameters are important. This is the normal pressure and the tool workpiece interface temperature. As regards determining the normal pressure, we used an L.S. Steiner 2D model, where we modeled the 3 deep drawing operations, the first deep drawing, the redrawing, and the second redrawing, transferring the results for accumulated effective strain and thereby increasing flow stress from step to step. In the final critical redraw, second redraw operation, we got this picture for the radial stress distribution in the workpiece as well as the tool, and we reached a maximum pressure of 900 megapascal, which has to be established then in the bending under tension test. This was done by designing a special form of the pin tool in the bending under tension test by confining the area of the contact to a smaller amount. Then we were able to reach the same pressure. Regarding the thermal analysis, unfortunately, I don't have a slide showing the calculations for the stainless steel used in the production, but I have a similar one for DP800s, which was a material investigated as proposed by SSAB. For this case, we reached a maximum interface temperature of 210 degrees. The long-term effect of temperature is difficult to assess in most of the laboratory test machines because the amount of time required between two consecutive tests implies excessive cooling of the tool if heating of the tool is not applied to ensure the typical working temperature. Moreover, and most importantly, is that a slow buildup of pickup, which only becomes significant after several hundreds of strokes, is what you normally see in industrial production. In order to improve the laboratory tests as regards these issues, a new universal triple test machine was built in our laboratory. The test rig was developed for performing bending and tension tests, draw bit tests, and sweep reduction tests. These three tests have proven feasible to simulate normal sheet forming operations. The special feature of the new machine is the possibility to run repeated tests from coil. The material is fed from a coil of more than 1 kilometer, which means that we can do thousands of tests in one go. We can adjust the sliding length, the speed, the cycle time, and the total number of strokes in order to emulate the conditions in the production. And we can preheat the tool temperatures to keep a level which is similar to production. It was decided by our industrial partner to support us in developing and constructing this equipment, which we, of course, are very grateful for. Here I show a video of a close-up of the bending under tension test. We do the same sliding length as in the practical production test, 20 millimeters, as far as I remember. Now we are homing the hydraulic claws and repeat the test. Typically, we run this for 1,500 strokes because industry has realized that if a lubricant can withstand 1,500 strokes without pickup and galling, then it's a promising lubricant. Here we see an overview of the test. The hydraulic clamp during the front tension is driven by a ball screw, which is rotated by a hydraulic motor, which you cannot see. It's situated behind here. The machine is controlled by a PLC over here, and this PLC can be programmed by a LabVIEW program on a PC computer, which we show here, and where we also have takeouts during testing of the individual parameters such as front tension, back tension, and frictional torque. This slide represents some test results. We have here test results for the steel used by Grundfos in the production, and it's lubricated with an environmental friendly oil from Rhenus. And we see the blue curve representing the torque is very stable throughout the 1,500 test strokes. And that goes for the front engine as well. After 1500 strokes, we have a very nice tool surface with no sign of degradation or pickup, and the good performance of the new lubricant was challenging us to increase the test rate to 95 strokes per minute with the same results as 40 strokes per minute. Wherefore, it was also tested in production and turned out to be possible without problems, so that we can actually now increase production rate from 40 to 95 strokes per minute with the new oil, which was not possible with chlorinated paraffin oil. The other test of lean duplex steel resulted in bad performance, but this is also a much harder steel, and we see heavy pickup already after 33 strokes, and an increase in load as well as frictional torque. The next issue I will talk about is single point incremental forming. In 2005, we started research on single point incremental forming. And as an example, we here see a small student project on producing a silencer house for a Volvo truck in a somewhat modified version. So the sheet is clamped in a rig, which is moving according to numerical controlled XY table. And here we have the rotating pin. This is difficult to produce in stamping because of the slope here, so that when you try to stamp, initially you have very small contact area between tool and workpiece, and this will lead to cracking. Already in the early days of SPIF, before we started, it was realized that forming limits in SPIF were much larger than in conventional forming. This is an FLD curve showing the FLD curve for annealed aluminum, pure aluminum, and at the same time showing the forming limit curve for incremental forming of the same material. And we see a vast increase in formability when we do SPIF. There was a long-term dispute among researchers on SPIF to explain the reason for this. But we found that it was not satisfactory. So we started our work on SPIF and did it in close collaboration with Paulo Martin's research group in University of Lisbon. And in 2008, together we developed a theoretically based explanation to the significant increase in forming limits. They were due to the fact, we think, that we don't have necking instability as a problem in SPIF, so that we can form all the way to fracture. And in order to verify that, we set up a membrane analysis of the local plastic deformation in different zones in SPIF under plane strain condition and equibiaxial strain condition here. We calculate the stresses and the hydrostatic stresses. Here we see a forming limit diagram of aluminum 1050 in semi-hard condition. And the forming limit curves are determined by tensile testing and two types of bulge tests, one with an elliptical die, one with a circular die. If we continue the deformation in the bulge test here, we see that after the balanced biaxial stretching till instability, there is a kink in the strain path. Since after that instability, we have plane strain deformation, and fracture occurs much later. The other experimental points here are determined by single point incremental forming a truncated cone as well as a truncated pyramid for two different sheet thicknesses, 1 and 2 millimeter. Our theoretical model of the forming fracture curve is based on IDA's ductile damage criterion. And it determines this curve with a slope given as a function of the tool radius and the thickness of the sheet. And we see rather good accordance with our experimental points here. My final subject to talk about is modeling and testing of resistance welding. In 1993, Danfoss approached us to establish a joint project on numerical modeling of resistance welding. And this resulted in a long-term collaboration in our development of a Fine-Element program on resistance welding. We developed a model including 4 calculation models: a thermal model calculating heat transfer and temperature distribution, an electrical model calculating current and voltage distribution as well as heat generation, a mechanical model calculating stress and strain distribution and geometry of workpieces and contact interface, and finally a metallurgical model calculating temperature-dependent material properties and possible phase transformation. Especially the work on the mechanical model, we got great help from Professor Paulo Martins, and he is still participating in the ongoing development of our program SORPAS, called Simulation of Resistance Projection and Spot Welding, which is developed by my former postdoc, Wenjie Chang. Here we see an animation of a 3-sheet spot welding on a DC machine, where the purple and later black zone is the weld nugget. I can show the animation once more, like that. And in 1999, Wenjie Chang established his company, a Danish company called Swantex Software and Engineering, to market the code to industry. Here are some examples of his work. The first one, together with us, studying spot welding of stainless steel to mild steel. And we see the characteristic shape of this weld nugget is rather well found in our simulation. The second case was provided by PSA, who wanted to see if SORPAS could do what they couldn't do with their own modeling. And so we did a blind test where we had to simulate the spot weld of 1 millimeter high strength steel, that's the upper one here, to 2 layers of 0.7 millimeter mild steel, a typical joint in automotive engineering industry. Only after we provided this simulation to them, they send us their material graphic study of the weld, and based on the very nice agreement between the two, they decided to to buy a license of Sorbus. The Sorbus code was originally developed as a 2D code, which enabled analysis of spot welds and projection welds, single welds. In automotive industry, we typically have multiple spot welds and also projection welds. And when we have multiple welds, we have the problem of shunting effects, where part of the current from the second and third weld are running through the first and the second spot. This means that after running the first weld, we got 5.75 millimeter weld nugget running with the same process parameters. The second nugget is 5.3 millimeter and the third is 5.04. So in fact, one should adjust the weld current to obtain similar size of the weld nugget. And this is now possible to predict how to adjust the current. Sorbus has become state-of-the-art in resistance welding, and this slide shows some of the many license holders in the world. We have a large number of automotive industry in Europe: Daimler, Mercedes-Benz, BMW, Volkswagen, Peugeot, Citroën, Renault, and Volvo. And in the US, Ford, General Motors, Chrysler, and US Honda. In Asia, we have Honda, Toyota, Hyundai, Mazda, and a large number of the largest steelworks in the world, or about half of the largest steelworks in the world are also using the code. Finally, I come to acknowledgement. First of all, many thanks to 130 master students and PhD students in their project work, 23 graduate students, 42 PhD students, and 23 postdocs. Also, thanks to the many different funding organizations in Denmark, as well as in EU, and private foundations and industries in all these countries have supported our work. I will also forward my thanks to 141 external co-authors from 24 industrial companies and 50 research institutes in 18 countries, some of which are mentioned here.